Welcome back, AP Calc AB students. Mr. Record here. We're going to take a look at our topic 8.3. We have a pair of examples that we're going to take a look at through two different videos. And if the content looks a little familiar, it's because it is. What I like to do with our topic 8.3, which is all about the using accumulation functions and definite integrals in applied contexts, is I break out the rate in and rate out problems that we saw just a couple of units ago at the very beginning to middle part of Unit 6. It's such an important part of the AP Calculus curriculum and ultimately questions that would appear on one of the free response questions on the AP exam that I like to hit it up twice. So we're going to take a visit to the zoo in our example number 1. So let's take a look here. In our problem, we are told that we've got a zoo sponsoring a one-day contest to name a new baby elephant. Zoo visitors will deposit entries into a special box between noon and 8 p.m. And the number of entries in the box t hours after noon is modeled by a differentiable function e for t between 0 and 8. Values that should be of e of t and hundreds of entries at various times t are shown in the table above. And so as you can see, you've got this table of 5 different times with the e, which is hundreds of entries. We're asked to do a variety of things to the problem, one of which, part A, is to use the data in the table to approximate the rate in hundreds of entries per hour at which the entries are being deposited at time 6. Show the computations that lead to your answer. And might I add that this is indeed a genuine released AP exam question from the year 2010, the operational exam. And this was problem 2 that appeared on both AB and BC. So part A, we've been here before. We've done approximations of this particular type of data where we want to figure out the rate in hundreds of entries per hour. And we want to do so specifically at time 6. Well, if you look in the table, it's like, well, there really isn't a time 6, unfortunately, with data. But we can do the next best thing and use the values around 6 and find our slope. Now, from a notation standpoint, it's really important that you start thinking about how you can best describe this. And so what you're doing is you're going to be taking the rate of E, also known in calculus as E prime, and you're going to evaluate that E prime at 6. It is an approximation. At this point, you can say that this is nothing more than E7 minus E5 all over 7 minus 5. Now, you wouldn't have to say E prime of 6 is equivalent or approximately equivalent. It's a bit of a stronger communication. I like it. You would, however, have to simplify, or not so much simplify, but evaluate these two functions, E at 7 and E at 5. So at some point, you would have to bring in the 21 minus the 13. Now, if a student were to have done this step as their first step on paper, that would be good enough to earn the point for the difference quotient, and it's likely enough to earn the point for the actual slope itself. In other words, we don't have to simplify this. We don't have to call this 8 over 2, which of course is 4, but we certainly can. We're told that this is measured in hundreds of entries per hour. It's likely that you don't necessarily have to attach that label. I'm not going to take any chances. I think it's a great idea, and we're going to do that. We're going to call this 400 entries, and then the per hour. Of course, if you don't want to write out the word 100, you could have put a couple of zeros after the 4, and then entries per hour. And that's all you'd have to do for Part A to earn full credit. Moving on to Part B. Use a trapezoidal sum with the 4 subintervals given by the table to approximate the value 1/8 times the definite integral from 0 to 8 of e of t with respect to t. Using correct units, explain the meaning of 1/8 integral e of t from 0 to 8 in terms of the number of entries. So there's two tasks that we need to do with this particular problem. The first of which takes us back a couple of units to the beginning of Unit 6 with our Riemann Sum Approach, and we're going to use the trapezoidal sum. So I'd like to start off by writing down the definite integral with the 1/8 coefficient to indicate, all right, I am going to approximate this thing. I'm going to say that this is approximately equivalent to something. Now, I am going to bring that 1/8 over because I am very fearful that I'm going to forget completely about him. And now I can focus on the definite integral from 0 to 8, which is where the trapezoid rule is going to get used. So next thing we do, of course, we know it's a trapezoidal sum. I might circle the number of subintervals 4, and I can see the table here is very conducive to using 4 such subintervals. Take note that the subintervals do not all have the same width apart, as we see 2, 3, 2, and 1. With the trapezoid rule, those are going to serve as the heights. So let's not forget that the area of a trapezoid, right, the area of a standard trapezoid is 1/2 times the sum of the two bases multiplied by the height. Remember that this idea of height is the distance between these values of t. The bases, in turn, end up being the consecutive pair of e of t values. So for our first rectangle, first trapezoid, we can write down our 1/2. We could also be clever and realize that 1/2 is going to be a part of every single trapezoid that we put together, so we could factor it out completely, and then we can just say we've got the sum of the bases, 0 plus 4 times the height, which is 2, and that would take care of the first trapezoid. We move on to the second one. 1/2 is still factored out in front. That's why I have this parenthesis here, this parenthesis right here. And so if I go to the next trapezoid, it's going to be 4 and 13. That will serve as the two bases. And the height is going to be the distance between 2 and 5, which of course is 3. We continue that same process. We now have 13 and 21 serving as our bases. And the height between 5 and 7 is of course a 2. And then to wrap things up with trapezoid number 4, we're going to take 21 plus 23 and multiply that by our height, the distance between 7 and 8, which is 1. Now I'll close off the parenthesis that allows us to multiply the half through, and I'll close off the bracket that would allow us to multiply the 1/8 through. Now, at this point, if you choose not to do any simplifying, it is A-OK. You will receive full credit for your trapezoidal approximation. The only thing left to do would be to explain its meaning. Now, if you wanted to simplify this, you certainly would be welcome to do that. Just don't make any mistakes. It is a calculator-assisted problem, so the chances of making a mistake might be slimmer. But it turns out to be 171 over 16. If that doesn't work real well for you, the decimal equivalent would be 10.688 if we ended up truncating. Now, what does this mean? Well, let's look at a couple of things here. First of all, from a units perspective, E of t is measured in hundreds of entries. dt is measured in time, which is hours. So we have hundreds of entries times hours, which is a little weird. But then we have this 8 in the denominator of this constant out in front that serves as another time because it's just the same as the difference between your 8 and 0. So the hours will end up canceling, and your units are hundreds of entries. I'm just going to abbreviate that for now. But that doesn't do the full justice of explaining the meaning. What we hope that you really recognize is that from our earlier topic in Unit 8, 1 over b minus a times the integral from a to b is an average value. So you want to make sure that you use that phrase average. And the best way to do that is to say it is the, well, you could say the average value of E of t, which is the hundreds of entries, or in more plain, simple English, the average number of entries. Okay, expand on that. The average number of entries, what? Well, the average number of entries that were in the box, because that's where these entries reside. Okay, what is that answer? Well, it's 10.688. We know that. It's 10.688 hundreds of entries. And when did that occur? That's the last trick. You have to state the time interval. Well, that would be the average number of entries in the box between time 0 and time 8. You could say that, time 0 and time 8 hours, or if you model it by the fact that time 0 is noon and time 8 is 8 p.m., you could just simply say between noon and 8 p.m. And that gives you a nice description of what's happening with this problem. Very good explanation there using the NUT. All right, taking a look at part C. At 8 p.m., volunteers began to process the entries. They processed the entries at a rate modeled by the function p, where p of t is t cubed minus 30t squared plus 298t minus 976, hundreds of entries per hour. But these workers are only working between 8 and 12. According to the model, how many entries had not yet been processed by midnight, which is t equal 12, because these guys are getting tired. They want to go home, right? They're probably just volunteers. So what you're going to have to do is use the accumulation aspect of the definite integral. So we do know that if p of t is the rate at which entries are processed, then the number of entries that are processed would be the integration of p of t. But we're asked about how many entries had not yet been processed. So we better have a starting point of the number of entries, and then from that we can subtract the number that were processed. So I ask you at 8 p.m., how many entries were there? All one has to do is go back to the table and realize that the answer is 23. So you would start with 23, that is actually 2,300 entries, and then you'll subtract the amount or the number that is being processed. We only process between time 8 and 12. The rate at which we process is this p of t with respect to t, and then that's going to be our answer. Now, I am not going to move over to the graphing calculator and show you this setup because I've done that a number of times, and whether you're using a TI Inspire or a TI 84 and using Math 9 or the Inspire Shift Plus, you're probably in pretty good shape to be able to calculate this. It's probably in your best interest to take this P of T and go ahead and store it so that you can perform this calculation. In the long run, you're going to end up with an answer that actually works out pretty nicely. The integration of P from 8 to 12 is 16. And that's going to be equivalent to 7 when we subtract. And of course, the units are 100 entries. Again, you could put the 2 zeros after the 7 if you wanted to. And that leaves us with one more part. According to the model from Part C, at what time were the entries being processed most quickly? Justify your answer. Well, in order to pull this off, you're going to have to find a maximum of the rate at which things are being processed, right? At what time were the entries being processed most quickly? Well, the entries are being processed at a rate of p, so we want to find the maximum of p. In order to do that, you're going to have to set p prime equal to 0. And this might require a bit of calculator's use because I believe the answers are going to come up a little bit rough. So let's move over to the calculator and take a look at this. So here we are back to our calculator screen using the TI Inspire. Notice that I have the solution to part C up where I defined P of t and then performed my difference between 23 and the definite integral from 8 to 12. Now what we want to do is we want to solve when does the derivative of P equal 0. And so there's a variety of ways to do that. On a CAS calculator, perhaps the most efficient is to go to Algebra and choose Solve. You're going to have to take the derivative of your P equation, which is just the shift minus shortcut with respect to t, P of t. And we're going to take this derivative and we are going to set this guy equal to 0 and say we want to solve for t. And that should give us what we want. Now, a lot of times I like to put a decimal in there just so that I get some good decimal output. And that's exactly what has happened. And those are my two t values that I want to record. And thus, they're going to be candidates. Now, before we return to the document, we're going to go ahead and stay here with the calculator because we have to make a decision about what kind of extrema are we looking for? What kind of max? Absolute max? Relative max? Well, given the fact that we're talking about a closed interval from 8 to 12 of a real life situation, we're certainly looking at an absolute extremum. A lot of times on the AP exam, when you have contextual minimum or maximum that you're trying to find, and they don't provide the adjective, relative, or absolute, you're probably looking at an absolute extrema and therefore the candidates test. So all we need to do at this point is take these two values of t, use them along with our candidates, and we're basically going to put together a table of values. Best way to do that, with P being already defined, is I'll take P evaluated at 8. Okay, so at time 8, 0 entries have been processed. It's because our volunteers just came onto the scene and they haven't really gotten around to really counting things yet. But some time goes by and they're counting, and at time 9.1835, they've counted a little over 500 entries. And then they're going to continue to count, and they do so, a little bit more than an hour later at 10.8165. And we got P of 10.8165. And that gives us, now, they haven't really counted quite as many entries there. Their rate is not nearly quite as quick, I would say. Entries are not being processed nearly as fast, only at a rate of 2.9. Now, I should maybe reiterate this 5.08. It's a value of P, which is the rate at which entries are being processed. So they're processing 500 entries per hour. They're counting pretty quickly, but the night's wearing on and they're getting a little tired and they're slowing down. So again, this 2.9 would be 2.9 hundred, which is 290 entries per hour. Well, let's see what happens at midnight. Maybe they're getting a second wind and they're really working pretty quickly at midnight, and lo and behold, they sure are. They want to get this job done. So by the time the clock strikes midnight, they are counting entries at a rate of 800 per hour. So let's return to the document and write up all of our findings here. Now, Obviously, so much of this problem was done with the use of a calculator. So all of your answers are pretty much sitting on your calculator screen. So some of the things that you would have to port over. Well, you'd have to state the two values at which the p prime was equal to 0. This is very likely going to earn you a point. Make sure each one is expressed to at least, 3 decimal places. So that is taken care of there. You don't have to write down the candidates are, as long as those endpoints show up in your table of values. That would be certainly acceptable. And so we're testing t to find values of p of t, and those candidates are 0, 9.183, 10.816, and our 12. And it's very likely, depending on the year, that could earn the second point. Depends on the problem and how many other points are kind of masked into that particular free response question. Of course, you got values for P of t, and I do want to tell you, if you place values for P of t, they all have to be correct. Even say one of them or two of them that don't turn out to be your max. You can't have any erroneous values in your table, or else it's very likely that you could not earn the final answer point. And that final answer point is not just these values, but it's interpreting the fact that this 8 happens to be the largest value, and it wanted to know at what time was that happening. It didn't want to know, say, how fast the entries were being processed. They just want to know when that's happening. So we could just simply write up a narrative and say, okay, well, the entries are being processed, let's say, most quickly, being processed most quickly at time t equal 8. And it's probably a good idea that we state exactly what the units of 8, and that would be 8 hours, or even better yet, 8 p.m. is such a good descriptor because that takes care of the hour. I'm sorry, time, no, not time 8. See how I got tricked into using the 8 there? At time 12, which is midnight. Yes, so important. Now, again, if the question asked at what rate were the entries being processed most rapidly, then you would say 800 entries per hour. And so that would take care of the problem. That would give you full credit. Typically, this is worth 3 points, and that would be a perfect solution. Hopefully this helps out. We do have another problem coming up that's going to review another former AP exam question, I believe from 2012, I believe. Give you a little preview here coming up if you want to see it. It's this guy right here from 2000. Oh, this one's from 2010, and it's a wonderful snow shoveling problem. Make sure you check it out. Thanks for joining, and we'll see you next time.